Hello, I am Sudhakar Kumawat, a researcher at Osaka University. I will be introducing our paper on privacy preserving action recognition via motion difference quantization. This is a joint work with Professor Hajime Nagara at Osaka University. A typical action recognition pipeline consists of a dynamic scene, a camera system to capture the scene, and a recognition model to identify the action performed in the scene. In this work, our goal is to develop an efficient encoder for the camera system that allows the capturing of important features for action recognition while protecting actors' visual privacy. However, action recognition while preserving privacy is tricky. This is because action recognition performance strongly depends on the quality of spatial and temporal information, and if the resolution of either of these information is dropped for protecting privacy, the action recognition accuracy also drops. Here in the left example, downsampling may work for privacy preserving action recognition. However, in the right example, it may not work since the information about the number of fingers is lost. To solve this issue, we propose BDQ encoder that preserves both spatial and temporal information for action recognition while protecting actor visual privacy. The architecture of BDQ encoder is very simple. It consists of three modules: a blur module, a difference module, and a quantization module. The blur module is a Gaussian function with trainable standard deviation. The difference module takes the intensity difference of consecutive frames. The quantization module applies a pixel-wise learnable quantization function to remove the sensitive information. The parameters of BDQ are trained using the following adversarial training method, which consists of two iterative steps. In the first step, the privacy network's parameters are fixed and the BDQ and the utility network parameters are trained using the shown loss function. In the second step, the BDQ and the utility network parameters are fixed and the privacy network parameters are trained using the shown loss function. Here we evaluate BDQ on the SBO dataset. The SBO dataset have 8 action classes and 13 privacy classes. We observe that BDQ achieves better trade-off in comparison to other methods. Furthermore, its space-time complexity is significantly lower in comparison to that of the Wu method. We also evaluate BDQ on the KTH and IPN methods. The KTH dataset has 6 action classes and 25 privacy classes. The IPN dataset have 13 action classes and 2 privacy classes. The results obtained are similar to the ones obtained on the SBO dataset. We study the contribution of each of the components of BDQ in preserving privacy. We observe that as the value of alpha increases, the quantization intervals merge, leading to a faster decline in the action recognition accuracy compared to the privacy accuracy. Here we show that BDQ consistently preserves privacy features across multiple image classification networks. Note that BDQ encoder used in this study have seen only the ResNet 50 network during its training. Similar to previous study, here we show that BDQ consistently produce features that are useful for action recognition. Note that the BDQ encoder used in this study have seen only the ResNet 50 network during its training. In this study, we show that BDQ hinders reconstruction of the original scene from its output. To prove this, we train a 3D unit model with input as BDQ output videos and labels as original videos. We observe that a trained BDQ hinders reconstruction by the 3D unit network to a good extent. In this study, we show that BDQ performs at par with dynamic vision sensors. To prove this, we simulate a DVS sensor with varying threshold and use its output for action and privacy recognition. We observe that the DVS sensor at threshold 2.4 behave similar to BDQ at alpha value 2. Thank you very much for listening. Please scan the QR code for the code. Thank you again.